Greetings, learners of calculus. This lecture will be on exponential derivatives. In other words, derivatives of exponential functions. Recall the graphs of exponential functions. Use the graph of each function to predict the graph of its derivative. So your most basic form of an exponential function is some constant b raised to the x, where x is the independent variable. Now we want this constant to be a positive constant, cannot be 0, cannot be negative. We also don't want that constant to be 1. Recall that we refer to this constant as the base and the x as the power or exponent. In this case, it's the independent variable. An exponential function is not the same thing as a power function. 2 to the x is an exponential function, but x squared is a power function. It all depends on the position of the independent variable versus the constant. Now you get different looking graphs depending on the size of the base. Using technology, I've typed in f of x equals b to the x and then created a slider for b from 0 to 4, step size 0.1. b is 0, then we do not have an exponential function. We do not want the base to be 0. As b increases, we start getting exponential curves. When b gets to 1, again, we do not have an exponential function. This is just a horizontal line. But when b goes more than 1, we get these curves. In summary, if b is a value between 0 and 1, we have what's called a decaying exponential function that's decreasing from left to right. And if b is more than 1, we have an increasing or growing exponential function that is increasing from left to right. In both cases, the x-axis serves as an asymptote, and the outputs are only positive outputs. And notice, furthermore, that all of these exponential functions pass through the point 0, 1. That is because a legitimate base b raised to the 0 will give you 1, no matter what that base is. So in our notes, we have the point 0, 1. If the base is between 0 and 1, then we have a graph that represents exponential decay. And if the base is more than 1, we have a graph that represents exponential growth. Here we have a graph specifically of y equals 2 raised to the x. We'll use this graph to predict what its derivative looks like. Using technology to visualize the slopes, notice on the left side of this graph, the slopes are positive but small. And as we move to the right, the slopes become increasingly more positive. So I'll draw a few tangent lines in our notes. So here the slope is positive but small. Here the slope is still positive. In fact, the slope is always positive, but it's bigger. At this point, I extended the tangent line a little bit longer so I can predict what numerical value it'll be. But if we go right 1, it doesn't look like we go up an entire unit, maybe up only 0.7. So I'll guess at this point that the slope is about 0.7. And then it just keeps getting bigger. If we really predict that the slope when x is 0 at this location is about 0.7, then the graph of the derivative should have an output of about 0.7, so roughly there. And let me remove the tangent lines. At this point, go right 1, and we go up about 1.5. So I'm guessing that the slope of the tangent line is about 1.5. And so the output of the derivative function should be about 1.5 when x is 1. If we were to repeat this, we would see some sort of derivative function that appears to be pretty similar to the original function. Now here we have y equals 0.5 raised to the x. So this is a base between 0 and 1, which is why we see a decaying exponential. You can also write it this way, 1/2 raised to the x. And since 1/2 is the same thing as 2 to the minus 1, you can write it this way, and then you can multiply the negative 1 in x. So all of these functions are the same. In particular, this last one, 2 to the negative x, reveals the fact that 0.5 to the x produces a graph which is a reflection of 2 to the x about the y-axis. Here is a graph of 2 to the x reflected around the y-axis. You get a graph of 2 to the negative x. But in this case, it is clear that the slopes are all negative this time. And by that symmetry, I can guess that at this y-intercept, that the slope of the tangent line should be about negative 0.7. So putting an output of the derivative function about right there. Here I expect the slope to be about negative 1.5, putting an output roughly here. With technology, here's a graph of 2 to the negative x, or 0.5 to the x. And you can see that the slopes are all negative, very negative, but become less negative as we move left to right. The slopes flatten out, approaching a slope of 0. So I expect outputs of my derivative function to be very negative, to become less negative, but to get closer to 0. In fact, with Desmos, we have the function typed in, we have a base chosen. You can also type in f prime of x, and Desmos will graph the derivative. And you'll notice that the red graph is a decaying exponential, and its derivative is below the x-axis. So the fact that we have negative slopes all across this red curve means that we have negative outputs for the graph of its derivative. And as we let b change, Here's when the base is 2. Blue graph is similar to what we guessed in our notes with the orange graph. And notice as the base continues to increase, there seems to become a moment where the two graphs appear to be identical, but then no longer. This seemed to be around 2.7. Of course, if you zoom in, you will see that the graphs are not identical when the base is 2.7. More on this later. Use the limit definition of derivative to find each derivative below and compare with your predictions above. In the first case, the derivative of 2 to the x. The limit definition says we'll do a limit as h goes to 0 of this function evaluated at x plus h. So change the x to x plus h, and then minus the original function, and then all over h. Now recall we can use a property of exponents. If you have x squared times x cubed, you can add the exponents to become 5. We'll use this property backwards. So 2 to the x plus h can be written as 2 to the x times 2 to the h. And then we have minus 2 to the x all over h. Now I can factor out a 2 to the x, leaving this expression. Now we're going to use technology to explore what happens to this portion as h shrinks to 0. So I have a slider for h, type in 2 to the h minus 1 over h, and now let's choose h values that are getting closer to 0. 0.1, 0.01, 001, and as I get smaller, we see that we're getting closer to a number that's about 0.693. This will be true if I use negative h's as well and make them get smaller. It turns out that this expression in orange does have a limit as h goes to 0, and that limit is the natural log of that base 2. If I type in natural log of 2, notice we get the 0.693 figure. Thus, the derivative of 2 to the x will be 2 to the x, this one right here, times the natural log of that base 2. Here's a graph of 2 to the x. Now I'll graph its derivative. This falls in line with our prediction, and with technology, it matches the graph of f prime of x. The orange and the purple are the same function. Now this second case, we have the limit as h goes to 0 of 0.5 to the x plus h minus 0.5 to the x all over h. Similarly, I can break up this first exponential into 0.5 to the x times 0.5 to the h, and then minus 0.5 to the x all over h. I can then factor out the exponential 0.5 to the x, leaving 0.5 to the h minus 1 all over h. Exploring this one with technology, we have 0.5 to the h minus 1 over h. We will let h get closer to 0, and notice this time our limit appears to be about negative 0.693. In fact, it turns out that the limit is the natural log of this base, 0.5. So this portion of our expression approaches the natural log of 0.5, which is the natural log of 1/2, which is the natural log of 2 to the minus 1. And if you remember your log properties, I can bring that negative 1 down as a coefficient and write this as negative natural log 2. That's why we're getting the exact same decimal we had before, but the negative of it. So approximately negative 0.693. So in the end, this derivative is 0.5 to the x times natural log of 0.5. Okay, you may have picked up on a pattern here. The derivative of an exponential function will be itself times the natural log of the base. We'll summarize that on the next page. The derivative of an exponential function is as follows. So this is a derivative with respect to x, so x is the independent variable. We are assuming that we have an exponential function with a base b that's constant, satisfying these conditions, must be positive but not 1. And in that case, the derivative will simply be itself, the same exponential function, times the natural log of that base. Find the following derivatives. Well, the derivative of 3 to the x, therefore, is simply itself times the natural log of 3. In this next example, we have a change of independent variable to y. It's better to rewrite this one. 1 over 4 to the y can be rewritten multiple ways, including writing it as 1/4 raised to the y. And this is what we're going to differentiate. Well, this is just a constant raised to the independent variable. So the derivative will be itself times the natural log of 1/4. I could write this as 4 to the negative y times the natural log of 4 to the minus 1, and then use that log property where this negative 1 comes down as a coefficient. So an alternate way to write this derivative would be negative of 4 to the negative y times natural log of 4. Any of these is acceptable for the derivative of this function. And the derivative of e to the z with respect to z would give us the exponential function e to the z back times the natural log of e. Well, this simplifies. Recall that the natural log is a logarithm whose base is e. So if I make the claim that the natural log of a is equal to b, This natural log is a logarithm whose base is e. This suggests and is suggested by the fact that e raised to the b is the same thing as a. Therefore, the natural log of e, if I say that this is equal to b, and the natural log has a base of e as well, this suggests and is suggested by the fact that e, this e, raised to the b must be equal to this e. In other words, that b must be a 1, which tells me that the natural log of e is just 1. So in other words, the derivative of e to the z is simply e to the z, which means that when the base is e, the derivative function matches the original function. So looking back, we saw that as I dragged this slider to around 2.7 is when the two graphs looked alike, although if you zoom in, they are not. It turns out that if that base is e, that the original function and the derivative are identical. This is one reason why Euler's constant e is so significant. We'll discuss this a little bit more later in this lecture. 3 more derivatives on this page. Here we have 3 functions being added together, so I can differentiate term by term. Here we have a constant times a function, so I can factor the constant out and then only worry about differentiating the function next to it. For this middle one, be careful you avoid the temptation of multiplying the 2 and the 5 to make 10 to the x. The x is only a power on this 5, but the minus 2 can be disregarded for a moment, and I can just differentiate the 5 to the x plus, and then I need to differentiate x raised to the e. Now, this is the constant to a variable, this is a constant to the variable, but this is a variable to a constant. So you have an exponential function, another exponential function, but this last one is a power function, not exponential. So for the first 2 derivatives, I'll use exponential rules, but the last derivative, I'll use the power rule. So we have the 3, and the derivative of e to the x is itself. That's the special case. Minus 2 times, and then the derivative of 5 to the x is itself times natural log of 5. And then plus, and then we use the power rule here. The constant e drops down as a coefficient, x repeats, and the power is 1 less than it used to be. Now again, be careful you do not multiply this 2 and 5 and say 10. Okay, this next case, we have u as the independent variable and a few u's here. I do see a product, so I want to split this. Now u is already taken as the independent variable, so I'll use v and w to represent my 2 factors of the product. And the product rule would be v prime w plus v w prime. So in this case, the derivative of v is a power function. Use the power rule, we get 10u times the second, 7 to the u, plus v, 5u squared, and then times the derivative of w, which is an exponential function, and it will be 7 to the u times natural log of 7. Now because the 7 to the u is present in both terms, we could factor it out along with other things. I could factor some u's and some 5's as well as the exponential. So 5u, 7 to the u, factor it out. That would leave 2 plus u times natural log 7. And here's a factored version of this derivative. In this last example, w is the independent variable, and here's w again. Fundamentally, this function is the tangent of another function. So we need the general tangent rule here. And that rule is the derivative of tangent is secant squared of the same argument, but then times the derivative of that argument. So this 8 to the w represents this inner function u. So to find the derivative of this expression, we need a secant squared of the same argument, 8 to the w. And then we need to put the derivative either here in front or here at the end, you choose. I'll put it in the front. The derivative of 8 to the w is itself times the natural log of 8. Okay, let's go to the next page. On this page, we explore the significance of y equals e to the x. So we're going to input some coordinates. X will be the input, y equals e to the x will be the output. And as we saw a moment ago, that the derivative of e to the x is itself. So plug in -3 for x, we get e to the minus 3, which really means 1 over e cubed, which is about 0.05, corresponding to this point right here in our graph. E to the minus 2, which is 1 over e squared, it's about 0.135. So it's gone up, corresponding to this point in our graph, which is slightly higher than the one to the left of it. Then e to the minus 1, which is 1 over e, which is about 0.368, corresponding to this point. E to the 0 gives us our y-intercept, which is 0, 1. E to the 1 is just e, about 2.718, giving us this point. E squared is about 7.389. E cubed is about 20.086. And one more, e to the 4th is about 54.598. Now, because this function has a derivative that is equal to the original function, all of these can just be copied and pasted into the tangent slope category. In our drawing over here, I'll graph just 3 tangent lines. The first one will be corresponding to when x is 0, The point is 0, 1, and the slope of the line is also 1. I'll draw a tangent line when x is negative 1. The green point is approximately negative 1, comma 0.368, and the slope of the tangent line is also 0.368. In drawing one more when x is 1, the point we are passing through is 1, comma e, and the slope of that tangent line is e. What's significant for every point along this curve is that the y-coordinate and the slope of the tangent line at that point always match. The y-coordinate and the slope match. The y-coordinate and the slope match. Using technology to look at a graph of e to the x, pick any x-coordinate like negative 0.5. This y-coordinate is also the slope of the tangent line. When x is 0.5, this y-coordinate, 1.64872, is also the slope of this tangent line. So this is a very interesting function. The outputs are also always the slopes of the tangent lines. And then finally, let's do this last step here, which is find the equation of the tangent line at x equals 1. So that's the blue one. So use this information. Our point slope form is y minus y1 is equal to m times x minus x1. Well, the y-coordinate is e, and the slope is e, and the x-coordinate at that point is 1. So we get an equation, y minus e is equal to ex minus e, and add e to both sides, and we simply get y equals ex, suggesting that the y-intercept of this tangent line happens to be 0, which appears to be the case in my drawing, that the blue line crosses the y-axis at the origin. Okay, let's go on to the next page. So on this page, we're going to explore the effect of the chain rule when we do compositions involving exponentials. Express the function as a composition y equals f of g. Then use the chain rule to find its derivative. So I have a function that's 5 raised to another function. This exponent I will consider to be my g of x. So g of x is equal to 2x cubed plus 1, suggesting that the function into which we are composing must be 5 to the x. Sure enough, if you take this function g and you substitute it into the function f by replacing this x with it, you will get our function y. So y is in fact the composition of f composed with g. Check. Now let's find the derivatives. G prime of x would be using the power rule, 6x squared. The 1 would go to 0. And f prime of x is the derivative of 5 to the x, which is 5 to the x times natural log 5. Now the chain rule from previous lessons suggested that to differentiate this function y, which is a composite function, f of g, that we would do f prime of g of x and then times g prime of x. So I'm going to take g of x and compose it or plug it in for all the x's in the f prime function. So that would give me 5 raised to the and then 2x cubed plus 1 and then times the natural log of 5. So this portion right here represents f prime of g. And now we need to multiply this by g prime of x, which is 6x squared. So we can generalize this process and form two general exponential rules. If you want to find the derivative, where x is the independent variable, b we're assuming is a constant that satisfies these conditions, and then u we're assuming is a function of x, or whatever the independent variable might be. That the derivative of this will be the same rule for just differentiating b to the x, which is b to the x natural log b, except instead of x, you keep that function u up there, and then the chain rule suggests you now multiply by u prime. The order in which you write these three terms does not matter because multiplication is commutative. Now, in particular, the derivative of e to the u, e to a function. I could use the formula we just wrote, in which case it would be e to the u times natural log of e times u prime, because I just take this more general formula, but specifically change b to e. However, this one will simplify a little bit more because the natural log of e is equal to 1. So the derivative of e to the u only needs two pieces, u prime and e to the u. I'll put the u prime first this time. Again, it doesn't matter if you write it first or second. Okay, find the following derivatives. The derivative with respect to y, this is a constant raised to a function. This is an exponential for which we need to use the generalized exponential rule. If you think of this function square root of y as u, then our rule would say that we need to repeat 3 to the u again. We'll need a natural log of the base, and we'll need a u prime. It doesn't really matter the order in which you write these. I'll put the u prime first. The derivative of square root of y with respect to y is 1 over 2 square roots of y, and then I'll write the 3 to the square root of y, and then the natural log of 3. If you want, you can write this as 3 to the square root of y times natural log of 3 all over 2 square root of y. Middle case, w is the independent variable. I see it there. I have a constant times a function, so we can ignore the constant for the moment, and I'll write 1 over w as w to the minus 1. and this is what we need to differentiate. W to the minus 1 is a function of W. You can think of that as our U. And the derivative formula will tell us that the 7 would stay, and the derivative of e to the u is u prime e to the u, as we discussed right here. So the 7 stays. I'll put the derivative of w to the minus 1 first. That derivative is negative w to the minus 2 using the power rule, and then I rewrite e to the w to the minus 1. Now I could rewrite this. We'll have negative 7 over w squared times e to the 1 over w. Or you could multiply this to the numerator and write this as negative 7 e to the 1 over w all over w squared. In our third case, x is our independent variable. We have the general structure of a function raised to a constant power, suggesting the generalized power rule. So that constant would drop down, the function would repeat, the power would drop by 1, and then the chain rule times the u prime. So the 3 drops down, the base stays the same, the new power is 2, and now we need to multiply by the derivative of the base. I'll need some parentheses. The derivative of x is just 1 plus, but now I need to differentiate this 8 to the cosine of x. You can think of this cosine of x as some function v. So if I differentiate 8 to the v, where v is a function, I would get itself, natural log of 8, and then v prime. These are the 3 pieces I need when differentiating a constant raised to a function. And so we're going to get 8 to the v again, and then times natural log of 8, and then times the derivative of cosine of x, which is negative sine of x. Now I'll rewrite this with just one minor step of simplification, and that's this negative and this addition. I'll switch to subtraction, giving this as a final result. Okay, and moving on. A population is modeled by the logistic function below, where t equals 0 corresponds to the start of the year 2020 and is measured in years, and capital P, which is our function, is measured in millions of people. Use the model to predict the size of the population at the start of 2035 and to predict the rate of change in the population at that time. Okay, so this function actually outputs population sizes as time advances. To answer the first question, what is the population at the start of 2035, I simply have to get a y-coordinate, or an output of this function. Now we're told that t equals 0 corresponds to 2020, which means t equals 10 would be 2030. T equals 20 would be 2040, and then 2050, and 2060. Now we want 2035, which would be t equals 15, in other words, 15 years after the start of 2020. So this point on our curve, if I can get the output, that will answer the first part of this question. So plug in t equals 15 into the population function and evaluate. We have a 5 in the numerator divided by 1 plus 4e to the negative 0.2 times 15. Negative 0.2 times 15 is negative 3. And then reaching for a calculator is this decimal. This is measured in millions of people. So if you wanted to actually give people, you would have to multiply this by a million, which is a 1 with 6 zeros. So we need to move the decimal to the right 6 spots. And then rounding to the nearest person, giving us about 4,169,626 people. And now we are to predict the rate of change of the population at that time. Well, rate of change will be a slope in this context, and the rate of change at that moment in time would be an instantaneous rate of change. In other words, the slope of a tangent line, which I've drawn here, and our goal is to find that slope. So we got to find the derivative next. I'll take the approach of rewriting p of t is equal to 5 times parentheses 1 plus 4e to the negative 0.2t, all raised to the minus 1. So I just brought this entire numerator, put it next to the 5, but with a negative 1 power on it. Now I can use the generalized power rule. So p prime of t, this negative 1 will multiply to that 5, giving us negative 5. The base will repeat. The new power will be 1 less than negative 1, so negative 2. And then the chain rule, we have to multiply by the derivative of the inside. Well, the 1 will go to 0, the 4 will stay, and the derivative of e to the negative 0.2t is itself times the derivative of the exponent, giving us this result. The negative 5, the negative 0.2, the 4 can all multiply. That gives me a positive 4, then times this exponential, and then this negative exponent will push that base back down to the denominator with a positive power on it. So to find the slope of the tangent line, I now need to find p prime of that time 15. And I'll go straight to a calculator for this. And we get approximately this decimal, which unit would be millions of people per year, because it would be the unit of the vertical axis, which is millions of people, per unit of the horizontal axis, which is measured in years. Now, if I want to get people per year, I simply have to move the decimal 6 spots and then round to the nearest person, giving me approximately 138,494 people per year is the rate of growth at the start of 2035. All right, and this concludes our lecture on exponential derivatives.